Now we're going to look at an ion that we probably haven't seen before, a type of ion that is able to also form an ionic compound, which are polyatomic ions. So just from that terminology there, we know that poly, the derivative in the Latin, links to many, and atomic to do with the atom. These polyatomic ions refer to an ion with more than one atom. More than one atom in its structure. So here you can see 4 different polyatomic ions. So I've just circled the atoms that the ion is made up of, and then the charges are outside there. So the names of these are carbonate. Okay, so you can see that the presence of the carbon there is highlighted. Nitrate, likewise the presence of the nitrogen is highlighted by that name. We've got sulfate, once again linking to the sulfur. And then we've got phosphate, linking to the presence of the phosphorus. So I wonder if you can work out, and we'll go through this in class, what does the 8 represent then? What is, if they've all got 8 in their names as the suffix, what does that link to within their structure? So now we're going to move on to the compounds that these particular polyatomic ions can form. Okay, so let's start with carbonate. So we just draw it as it is. Now, this charge tells me that it is already an ion. Okay, so we want to look at the different other types of ions, and it would be cations that would be bonding with this particular ion, because you can see it's got a negative charge, so it's going to be attracted to cations of any sort, and there's going to be a certain ratio that goes along with that. So let's say, for example, we know that sodium has 1 electron on its outer shell, so when it loses that 1 electron, it becomes a positively charged ion and an electron. So sodium, the ion, has the possibility of bonding with carbonate, the ion. So if we have a look at the ratio of sodium to carbonate, we can see, okay, well, that's got a positive 1 charge. That's got a negative 2 charge. So it looks like I'm going to require 2 sodium ions for every 1 carbonate ion. So that would lead me into the formula for sodium carbonate as being sodium subscript 2 and then the carbonate. Okay, it's the same process as that shortened process that I taught you last time as well, where we can just cross those charges over. Okay, and so that would be a positive 1. So there's a 1 that goes here, and that would be a positive, or that would now be a 2. Okay, from the negative 2 charge. So we just see here that the ratio of ions can be deduced using this shortened method. Okay, so while we're on a roll with sodium, we might as well see what sodium compounds look like with all of these particular polyatomic ions. So we've got sulfate here. So now we know sodium loses that 1 electron, becomes the sodium ion, okay, and better write it the right way around, so the cation always goes first. We've got 1 sodium positive charge, we've got 2 negative charges for sulfate. So I'm going to need, once again, 1 more sodium to ensure that this is a neutral compound, okay, made out of ions, but still overall it's going to be neutral. So once again, we're going to put sodium, sulfate. Okay, simple as that. If we keep moving and we have a look at nitrate, for example, okay, and we'll use sodium again as our example. Sodium +1, nitrate has a -1 charge, so therefore it looks as though they're going to only need one of each in the ratio in order to have a neutral compound. So that's the formula for sodium nitrate. Last but not least, we've got phosphate, okay? There's a formula for phosphate. So sodium, once again, has a +1 charge, okay? Phosphate has a -3 charge. So here it looks like we're going to need 3 sodium ions for every 1 phosphate ion. So that means we're going to have to write in the formula as sodium 3 phosphate. Okay? And that's really how we write the formula for polyatomic ions. It gets a little bit trickier, as we know, okay, when we've got 2 different charges that perhaps are not as simple as, you know, a 3-to-1 ratio or a 2-to-1 ratio, okay? So let's have a look at magnesium, just as our example from our group 2 element. So it's got 2 valence electrons, loses those to become magnesium 2+, and those 2 electrons. So once we've got the ion, we can then have a look at magnesium forming ions with, say, phosphate. Let's have a look. Okay, so this is not going to be as simple as some of the others we've encountered here. This has got a +2 charge. This has got a -3 charge. So if we add another magnesium, this is now 4-to-3. Add another phosphate, 6-to-4. Add another magnesium. Okay, now we've got 6-to-6. So it almost looks like when we've looked at the formula for aluminium oxide, but in the opposite manner. Okay, so how would this formula be drawn? We've got 3 magnesiums ions, okay, for every 2 phosphate. Now to write 2 phosphate, it wouldn't make much sense to write 42 or 4 and the 2 straight after, because that looks like there's 42 oxygen atoms within that ion. Okay, so that's not going to happen. So what we need to do is we need to say, well, there's 2 of those phosphates. So there's the use of the brackets. Okay, so this tells you how many of those ions are involved in this compound, or the ratio of those ions. As we know, it's a ratio. Okay, if we were to do another example with magnesium, you've got magnesium. Let's say we've got some magnesium carbonate. Okay, well this is back to being a simple ratio because that's 1-to-1. Okay, it's got an even, or the addition of those 2 charges becomes neutral 0. So magnesium 1 ion, carbonate 1 ion. Okay, same thing. If you cross it over, then it'd be 2 and 2, and we always use the simplest ratio. Okay, so if you were to use the crossover method, and it crossed over and it was magnesium 2 and carbonate 2, then we'd always simplify that, as we do with ratios, to the smallest ratio.